There's one more property of probability that's not listed in the book as a basic property, but it's so important and we're going to use it so much that I want to take the time to show it to you. It's very easy. You'll believe it immediately. And that is let's let A and B be events, that is subsets of a sample space S. So here's S, A, and B. Then the probability of A equals the probability of A and B complement plus the probability of A and B. A and B complement is right here. A and B is right there. So the reason this is true is that we said that sets A and B satisfy A equals A intersect B complement union A intersect B. Now if A, B, and S are finite, then this means that number of elements in A equals number of elements in A intersect B complement plus the number of elements in A intersect B. Now if we divide by the number of elements in S, then we have this equality. And by our discrete probability model, this is probability of A equals probability of A and B complement plus probability of A and B. So that's one of the ways we look at probability. Now if A, B, and S are regions in the plane, then instead of cardinality of S, well, cardinality of S would be infinite. We have area of A equals area of A intersect B complement plus area of A intersect B. And we can divide by area of S. And by our continuous probability model, this is probability of A equals probability of A intersect B complement plus probability of A intersect B. So let's do one example and see how this concept comes up. I'll write the claim again. Probability of A equals probability of A and B complement plus probability of A and B. Now a lot of times in probability we get lazy. Instead of writing A intersect B complement and A intersect B, we just write A and B. A and B or A and B complement. So this is just shorthand for the intersection. All right, for example, let's say our experiment is rolling a fair six-sided die. And let's let X be the outcome. Let's let A be the set 1, 2, 3, so the low numbers. And let's let B be 1, 3, and 5, so the odd numbers. Then the probability of A is 3 over 6, which is 1/2, because the sample space, of course, is numbers 1, 2, 3, 4, 5, 6, all possible outcomes. So the probability of A is the number of elements in A over the number of elements in the sample space, 3, 6, or 1/2. Also, we can divide up A into the elements that also belong to B and the elements that don't belong to B. So if we want to break up A, we can say a probability of getting a low number is the probability that X is less than or equal to 3 and X is odd, plus the probability that X is less than 3 and X is even. So in terms of A and B, this is the probability of X is less than 3 and X is odd, means that we're in A and B simultaneously. X is less than 3 and X is even means that we're in A but not in B. Either way you write it, we're breaking up A into two cases. The cases where we're in B and the cases where we're not B. So for in B, X is less than or equal to 3 and X is odd, looks like those are the numbers 1 and 3. I'll leave out the curly braces. Probability of getting a 1 or 3. Then if we're in A-B complement, that is X is less than or equal to 3 and X is even, looks like that's just 2. So the probabilities are 2/6 and 1/6. Two possible outcomes over the 6 total. One outcome over the 6 total, so think of a 2/6 plus 1/6, which is 3/6, which of course is 1/2, which we knew the probability of A was. So sometimes we're going to find it useful to divide an event into pieces, the pieces that belong to some other event and the pieces that don't belong to that event. The end.